yesterday, and Professor Z called L, I think. Capital R, okay. Now, omega, you know, it's the energy density divided by the square of the Hubble constant to make it dimensionless. We take a standard equation of state P is gamma minus 1 mu, which will give you dust. If gamma is 1, it'll give you radiation. If gamma is 4/3, and so on. And the Hubble parameter. And then from this, from the equations we've had, you can easily deduce that S dot is H times S, and omega dot is H omega into 1 minus omega into 2 minus 3 gamma. And these gives you a phase plane for omega as a function of the scale factor. Now, this is really quite nice because we want to know how this evolves through the history of the universe. And for ordinary matter, that is for gamma greater than 2/3, you get a fixed point for omega is 1, the critical density. Now, that's obvious from here. When omega is 1, omega dot is 0, and so that is an integral curve. The line omega is 1. The line omega is 0 is also an integral curve. That's also obvious. When omega is 0, you get omega dot is 0, and when omega is 1, you get omega dot is 0. Now, if you just look at the signs of this and work it out, what you will find is if you are slightly above here, omega rises and it diverges. And so this is unstable, and this is what underlies what is called the fine-tuning problem that inflation tries to solve. If omega is a little bit above 1, it increases without end. If it is a little below 1, it decreases towards 0. And so this is an unstable line. It is an exact solution. If you are omega 1 at any time, exactly omega is 1, you remain with omega is 1 for all time. And that is absolutely independent of the equation of state. That is for all equations of state. But for ordinary matter, you diverge. Now, there's a problem with this diagram, and the problem is you can't see what happens to these curves as they go up. And in fact, omega diverges. I mentioned this briefly yesterday. Omega diverges when the universe reaches its maximum radius, because at that time the energy density is finite. But as you reach the top and you start recollapsing, the Hubble constant is 0. And at that instant, omega is infinite. Now, there's nothing wrong with the physics. You just have chosen a variable which is not a terribly good variable. Well, there's a nice way to deal with that. What we can do is we can take an arctan of the variable, and then omega is infinity becomes a standard line across here, as you can see there. And what you can do is you can just continue right through, and you get here the complete phase space. What you had above was a half phase space. And what you get here is for the models which recollapse, omega goes to infinity, which is when the model has reached its maximum. The radius scale function has reached a maximum. S dot is 0 at this instant. The Hubble constant is 0. Omega is infinity. And then it recollapses to this future singularity. So that's the past singularity, and that is the future singularity. And what this now gives you is a time in reverse invariant phase plane. In fact, for every expanding model, there is a contracting model in this diagram, and that's the complete phase space for standard matter for omega as a function of S. Now, if you have matter with gamma less than 2/3, the sign here changes, and you get the opposite effect taking place. What you get is that omega is 1 becomes an attractor. So it was a repeller up here, but it becomes an attractor here. And as the universe evolves, omega tends towards 1. And this is the famous solution that inflation gives you for the reason that the universe is very close to flat nowadays. It's because for an inflationary equation of state, which will be gamma less than 2/3, the omega is 1 acts as an attractor. Now, in fact, in inflation, what happens is initially, you probably don't have inflation, you probably have radiation, you might have a quantum era. What I've drawn here is the complete diagram of omega for an inflationary universe. Now, there's some initial period where you don't know what's happening because that's the quantum gravity domain. You then have an ordinary matter, a radiation era, when omega diverges from 1. Then a scalar field takes over, and this will be discussed for you by Professor Roy Martins later on, and then omega is pulled towards 1. At the end of inflation, the scalar field comes to an end, it gets converted to radiation, and you go back to an ordinary universe, ordinary matter, and then we reach today, that vertical line here, and the universe carries on to infinity. And so this is the phase plane. The omega diverges until inflation starts. It then gets pulled towards 1 as inflation takes over. At the end of inflation, it starts diverging again from 1, excepting if you are at the critical density, in which all of this is irrelevant. You stay at 1 for all time because you are at exactly that critical density. And this shows that completed again in the same way as before, with omega is infinity there. And it's quite... Now, we must take this with a little pinch of salt. I've done this as if the physics is time reversible. Now, the turning on of inflation and the turning off inflation is actually a process which is not time reversible. So you must take the upper half of this, which a little pinch of salt. That would only be the case if inflation turned off and turned on again in exactly the time reverse of the way it happened in the expanding phase. But you see a very interesting result coming in here. When you put the whole diagram in, you can see a fixed point here. It's an unstable fixed point because it is a saddle point. That occurs for omega is infinity. What is that? That is the time when the Hubble constant is 0. What could this solution be? If you think about it, it is the Einstein static universe. And what you see is in this model, there are two starting points. There is the diverging point, the Einstein de Sitter universe at the beginning, I've mentioned already. There is the Milne universe in the far future as the future attractor. And there is now the Einstein static universe, and there are solutions which start at the Einstein static, which asymptotically tend to the Einstein static, and that is the new feature we have here. And this is a completely non-singular state of the universe. This is the highly singular Einstein de Sitter state, but this is the Einstein static non-singular state. And so what you get to see here is the possibility of the universe models which I have recently been developing with Roy Martins and Jeff Murrigan and others, in which you start off asymptotic to the Einstein static, which is completely non-singular. You go into an inflationary expansion phase. The inflation comes to an end, and then what happens in the far future depends on what happens at that time. But in this case, it would recollapse and come back towards an initial singularity again, or an Einstein de Sitter, depending on this time reverse, which, as I've said, in fact, we don't expect the solution to be the turning on and off of inflation to be time symmetric. But the thing that you're seeing here is, firstly, the standard inflationary models. If they are less than 1, what you do is you get where omega increases, it decreases towards 0, and then it comes back towards 1, and then it goes down to 0 in the far future universe. If omega is greater than 1 for ordinary models, omega increases, decreases towards 1. It increases, it goes through infinity, and you enter your collapse phase. And what happens here depends on the time reverse dynamics. And you get this new possibility of a model which is asymptotic to the Einstein static in the past. It is completely non-singular. It expands into an inflationary era, then the post-inflationary era, and then what happens in the collapse phase depends again on the time reverse dynamics. And one point which I think I must make out of all of this, which is a lot has been made, and you will know about this, about how close omega is supposed to be to 1 today. What you can see is that is an unstable situation. Even if omega is very close to 1 today, unless you are at exactly the critical domain, this will not remain true. Either omega will go on to diverge or it will go on to 0. But in fact, in inflationary models, there is, even if however close omega is to 1 today, that is an unstable situation. You also see the following. Taking the models which start off at the Einstein static, choose a time today, like that time there. There exist inflationary models which will give you any value you like for omega today. There are models, as you can see from that phase plane diagram, that will give you any value you like. A lot of the inflationary literature is very confusing about this. It says inflation must lead to values very, very close to 1. Well, in fact, that is actually not really the case. Yeah. Yeah.
So now
the Einstein static model is completely unstable because it's a saddle point.
But I see these diagrams as like a stability analysis.
Yes.
And you say you find out, like, when you said you're developing a model which starts at Einstein static and it does the inflationary thing, so you have different solutions as you are moving along the fluid flows. And you say you use normally you solve the field equations and you get one solution out, like Einstein static or de Sitter or something. So now you're trying to find to match those different solutions to the field equations to have changing. I don't understand what you just said when the work you're doing with Jeff.
Well, I'm not sure if we should go into this in detail now. We'll be looking at this later on, I think. But I'm not sure. The solutions will join. There'll just be one solution, and there's no question it exists. The analytic approximations we will use for it at different times will vary, and that's where complication will come in. Okay, now, oh dear. Okay, now, I want to just make one other comment about the inflationary models, which is as follows. What you've got is you've got an energy density is a half phi dot squared plus v of phi, an effective energy density, and a pressure is a half phi dot squared minus v of phi. And you put them into the field equations which we had written down and which are in the notes that you've given. And the question is, how general is the behavior that is allowed? To put it another way, if I choose a scale factor a of t, let's just sort of choose when I invent a scale factor which I happen to like because it will have a behavior which I would like for some physical reason. The question is, can you find a potential which will give you that behavior? And the basic answer is yes. There is an inverse theorem which I developed with Mark Madsen, which you will find in Classical and Quantum Gravity, Volume 8, page 667, 1991, in which we basically prove the following. Choose A of t as you wish. Now, there is a reality condition which has to be satisfied, and one must be careful about that. But basically what happens is the following. You can solve the field equations we had before to give you V is equal to minus a third energy density of any radiation you have plus h dot plus h squared plus 2 times k over a squared times divided by h pi g, and phi dot squared is equal to minus 4/3 rho r plus minus h dot plus k over h squared over 4 pi g. You can run the field equations around to get it in that form. And here h is a dot over a, and then h dot is the time derivative of that. And what that tells you, you can choose a of t as you wish. And as long as this remains positive, you are getting a positive potential energy. And as long as that remains positive, or at least not negative, you are getting a real kinetic energy. So you can choose your a of t as you like, and from those equations you can find v of phi and phi of t, which gives you an exact solution of the Einstein field equations, no slow rolling approximation. And this is a way in which you can, in fact, take any behavior you want and use the fact that v of phi is not known. In these equations, as treated in the inflationary physics community, v of phi is treated as a completely arbitrary function which can be given any behavior you like. And what this means is, in fact, through inflation, you can get any behavior you like, provided you satisfy the reality condition that that is greater than naught, and preferably this one is greater than naught, although some people don't mind if the potential goes negative. So this is just an interesting inverse theorem which you can use to construct exact solutions, and which we have used to construct exact solutions. In fact, this is one way which we have constructed exact solutions of the kind which we're talking about. Okay, now, in terms of dynamics, I have covered most of what I want to say. I want to just add in to emphasize that there is a non-singular model, inflationary model, which is, well, there are many, but in particular there's the one which we've been working on, which we call the emergent universe. And it starts off at Einstein static, and it goes to inflation, and then it goes to in a standard hot Big Bang. It has a very physical potential, and I think that Jeff will be talking about it later in one of the later talks at this meeting, so I'm not going to say any more about it, except to emphasize it is completely non-singular. It's totally regular. It's got a very nice physical potential. The only thing which the criticism which you can make about it, it is very special, and it's very special because it comes out of that Einstein static point we saw in that last phase plane. It requires a very, very careful balancing of initial conditions in order to start off from that initial state. And initially, the whole point about inflation was it was supposed to be combating special initial conditions, combating that kind of fine-tuning. Now, there's 2 points I want to make about this. The first point is that whether or not the real universe is fine-tuned is an open question. It is not a question which physics is able to settle. The initial conditions for the universe may have been set up in a fine-tuned way, or they may not. They may have been set up in a generic way, and we have no physical theory which can tell us which is what actually happened for the real universe. So fine-tuning, the fine-tuned, very special initial conditions nowadays is not philosophically fashionable. Some 20, 40 years ago it was philosophically fashionable, but the point is it is a philosophical question, not a physics question, whether the universe is fine-tuned or generic. The second point I want to make is something very strange is happening in the inflationary community. There is a group of people working on inflation who are trying to claim that inflation says that K is not exactly, that in fact the universes are exactly spatially homogeneous, and you will find a sub-literature of the inflationary literature which says this. This is very odd indeed, because inflation was supposed initially to be combating that kind of fine-tuning. That's exactly what inflation was about. And this is exactly the same degree of fine-tuning as we are getting in this non-singular inflationary model of ours. Because if you remember in that phase diagram, you are choosing that one very special model in which you're balanced to an infinite number of decimal places. Not a finite number, an infinite number of decimal places in order to get K is not exactly. That is an extreme degree of fine-tuning. And there is this strange part of the inflationary literature suggesting that this is what inflation says. I want to tell you inflation does not say that. Inflation has nothing to say about the sign of K. You can get inflationary models with +1, with 0, and with -1. And this model is infinitely improbable within the family of inflationary universes, and it should be treated as such. You can, if you want, to say that that is what you've got, but then you must say, I am choosing from all possible inflationary models an incredibly fine-tuned model as the one which I'm supporting, and there is no fundamental theory which tells you that this will in fact be the initial conditions for the start of that inflationary model. Okay, now, that ends that section, and we can get on. Oh, sorry. You've now got these notes, and I have some comments there on pages, what is page 120 and 121, about how these models relate to observations. And I'm not going to say much more about this, except to say there is nowadays a concordance model. And in this concordance model, the density of the lambda term, the effective density, is about 0.7. The density of baryons is about 0.02. The density of dark matter is about 0.3. And the total density is approximately 1. I emphasize approximately. And this concordance model, there is a great deal of evidence for, and I will be talking about it this afternoon in the public lecture, so I'm not going to say any more about that model at this particular time. There is a lot of evidence for it, which I will be briefly covering this afternoon. So, what I'm now going to go on to is, in these notes, section 7, the question of observations. And of course, cosmology means nothing without observations. So to look at the observations, you start off with our metric tensor, which we've been looking at before, minus dt squared plus a squared of t into dr squared plus f squared of r into d theta squared plus sine squared theta d phi squared. And you ask yourself, how do observations work in cosmology? Well, they work like in all relativity. We observe down the past null cone, down past null geodesics. A null geodesic will be a null vector, and it will be a geodesic. Now, in the Robertson-Walker models, because of their symmetry, we only need to look at radial null geodesics through the origin. Now, at first that might look an enormous restriction, only radial through the origin, but that is a generic geodesic because of the spatial homogeneity and the isotropy in these universe models. So you can put ds squared as naught, you can put d theta as naught, and you can put d phi as naught, and the basic equation for null geodesics there is naught from ds squared is minus dt squared plus a squared of t dr squared, because you put the d theta and the d phi to 0. And so you can solve that to say dr is equal to dt over a of t with a plus or minus. The plus or minus is the incoming or the outgoing null geodesics. And then you can integrate that. And that's the basic equation for null geodesics in a Robertson-Walker model. It immediately follows from the metric tensor of these space-times. Now, from that, you can deduce what you basically need, and I'm not going to do sort of a whole in-depth calculation of everything because they are in those notes. I want to just point out what the basic features are, and the first feature is redshift. And you've all heard about redshift, and that is 1 plus z is delta lambda, the change in wavelength over the wavelength emitted. And what you need for redshift is from here, in a couple of lines, what you do is you look at light emitted at an initial time, t, and then at a slightly later time, t plus delta t, te, t plus delta t emitted. These are received up here at to and to plus delta to, and what you calculate is delta to as a function of delta te, and that comes immediately from this equation up here, and the details are, well, it comes immediately out of that. That is, as it were, a simple exercise out of that, and the result is the one which is very, very well known. It is the scale factor at the time of observation divided by the scale factor at the time of emission. And this is the first very, very basic and important result in Robertson-Walker cosmologies. Redshifts are a direct measure of the amount of expansion that has taken place in the universe. And I want to just make a basic point about it. This is basically a time dilation effect. Basically, what is happening is that this period here, the period at the time of emission, is measured through this equation here to be slightly different from the interval at the time of observation. To get this result, you apply it to the period of an oscillating waveform, and it gives you the redshift. But this applies to all observations. So, for instance, if you're looking and you're measuring a quasar at a redshift of 4, and you see it varying on a period of some hours, for example, what you must do is you must realize there's a time dilation factor, and in fact you must change them and say it was actually oscillating at a rate which was a factor 5 times different from what you have measured. Everything you are seeing is changed by the factor 1 plus z. The small oscillations of atom that leave to wavelength are different, but also the macroscopic variations in intensity of light of any distant object are also different by exactly the same factor. That's the first point. And the second point is that this is the cosmological redshift. Now, this is the cause of one of the major problems in cosmology, that what we're assuming here is we are assuming that the emitter and the observer are both fundamental observers. They are both moving at exactly the right velocity. The problem is that your observer, your emitter, may be moving at a different velocity because there are random velocities in galaxy clusters. And we are also not moving at exactly the fundamental velocity. We are moving at 300 kilometers a second relative to the fundamental velocity. Now, the observed redshift can be written as 1 plus z Doppler at the emitter, 1 plus z cosmology, 1 plus z Doppler at the source. And there are actually also factors 1 plus z gravitational at the emitter and 1 plus z gravitational at the source. If you put it all together, you can get gravitational redshifts down there plus Doppler redshifts down there. You can get gravitational redshifts up here and Doppler redshifts or blue shifts depending on the case. And this is why the subject of redshifts is not as simple as you might have thought to begin with. You've got a lovely, beautiful theory in Robertson-Walker models for the cosmological redshift, but you can't observe the cosmological redshift. You observe a redshift, one redshift, and you have to split it up. How much was gravitational at the emitter? How much was Doppler at the emitter? How much was gravitation at the source? The observer at the source. This should be the observer, and that should be the source. Well, these we can handle. There's basically very small effects there, but one of the questions which has always been relevant: how big a Doppler shift can you get down there, and how big a gravitational redshift can you get down there where the source is? Now, in fact, a lot of theorems have been proved using general relativity that you can't get very great gravitational potential wells for stable sources, and most of the remaining discrepancy is when you look at a photographic plate at what looks like a cluster of galaxies and you measure the individual redshifts, you have to use astrophysical argumentation for each source to decide what is the cosmological part and what is the local Doppler part due to the local motion of those objects down there. And that's one of the reasons that measuring distances in cosmology is difficult, is because these random velocities give you random Doppler shifts, and so your observed redshift has to be broken up on the basis of astrophysical argumentation into the cosmological part and the Doppler part. What that means is you have to assign a cosmological average motion to that cluster, and then the individual galaxies you assign Doppler shifts relative to that average. That cannot be done by any fundamental principle. It has to be done by looking at the cluster and estimating its dynamics. So that's one of the reasons redshifts are not as easy in cosmology as one might have hoped. Okay, the second thing that you get is angles. And we look down at one angle, theta, and we look at another angle, theta plus d theta, an angle. And down there, that corresponds to some length L. And what you have to work out is what is that length L as a function of this angle? Well, what we do is we define something we call the observer area distance. And by definition, L is equal to alpha is equal to R0 times alpha. So we define the observer area distance such that the standard relation holds size is proportional to angle. But that just shifts the problem. We now have to go to our metric tensor and work out what is the actual, what is that quantity. So we have to use our Robertson-Walker metric to determine how distances go down there. And I'll just show you the starting step of this. The starting step is you go back to the metric tensor and say, down there, how do we work out from this metric what the distances are? Well, down there, we're going to be looking at a galaxy at an instant of time. So in this case, dt will be 0 because we will be looking instantaneously at the galaxy. And we will assume the galaxy is oriented orthogonal to our light rays, so it will be at constant r. And what you get left with is that part there. And what you can see then, just concentrating on d theta, you see there that ds squared will be to a squared times t f squared of r times d theta squared. That's for the area, and take the square root of that, the length will be a of t f of r times d theta. Now this is the time. When are we evaluating that? Down there at the time of emission. And so that's the basic formula which you compare with this formula here, and you work out that R0 is therefore the scale factor at the time of emission, times f of r. how do you then relate that to the actual geometry? Well, firstly, what you see is the spatial curvature comes in a very important way. Because what this is telling you is apparent angles as you move an object down the light cone. So for the same object, move it down the light cone, the apparent angle will be given by the size of the object divided by r0, where r0 is given by that expression. Okay, what happens there is f of r is sine of r if k is plus 1, it's r if k is 0, and it's hyperbolic sine if k is minus 1. And so you get a factor there in which the spatial geometry is changing the apparent size of this object out there. Now, additionally, the scale factor was different. We're looking down the light cone from here, where the scale factor was large, to there, where the scale factor was smaller. And to work that out, we've got to work out this expression here. But, sorry, what I should have also said is, of course, we have to work out r, which is the integral dt, integral from the time of emission to the time of observation dt over a of t, which is the formula that I worked out there. Now, you can do this two ways. You can take a particular solution and put in the function and work it out, or you can rewrite that as the integral at the scale factor at the time of emission, scale factor at the time of observation, dA over a dot, and then So what you do is you change variable from t to a, and so what happens is the a goes through, and then dt becomes dA over a dot, and then you substitute that from the Friedmann equation, because the Friedmann equation gives you a dot squared. And so what happens here is the matter, whatever matter you have chosen, feeds into the Friedmann equation. The Friedmann equation feeds in and determines a dot as you go down the light cone. This integral then tells you what this function r is, and you put it in there, and you get the apparent sizes. And that's quite a complicated kind of procedure. But it gives you a very nice formula, which is written down here, Matik's formula, area distance, for the case of p is 0 and lambda is 0, the simplest cosmological models. Go through this, and you can do it exactly. And what you get is what is written down here, 1 over h0, q0 squared, 1 over 1 plus z squared into q0 z plus q0 minus 1 into square root 1 plus 2 q0 z minus 1, close the brackets, close the bracket. It's a somewhat complicated formula, but from this you can plot the curves of area distance as a function of redshift. I've used the word area distances because given that we're in a Robertson-Walker, if lengths go like that, then areas go like RO squared times solid angle. So lengths goes as RO times angle, and Robertson-Walker model areas goes like RO squared times solid angle. And this formula you can use to plot curves, and you can go out and try and use this. In fact, we heard in Bruce Bassett's talk already how angular sizes are used in cosmology as tests trying to determine Q0. So it's from here, from this equation. Now, the single most interesting thing about this was discovered by Fred Hoyle in 1960, and that is that there is a maximum to R0. Now, that was quite unexpected until Fred Hoyle actually worked this out. What does it mean by saying there is a maximum? What it means is, if you take an object of given size and move it away, it looks very large to begin with, it looks smaller and smaller, and then it starts looking larger again. That is the apparent size of an object of given size as you move it down to higher and higher redshifts. As you move it down, its apparent size gets smaller and smaller, reaches a minimum, and starts getting larger. Wow, what's happening there? Well, what's happening there is our entire past light cone is getting refocused by the gravitational field of the universe. The light is moving out, and the whole light cone is refocusing. What is happening? The distance between two null geodesics is reaching a maximum and then is starting to decrease again, because all of the gravitational matter in there is pulling the light in and is causing the entire universe to act as a huge gravitational lens. And this is really quite exciting, because you can now say, look, For very, very distant objects, they're going to look much larger than you would have thought if you had used your naive expectations of Euclidean geometry. And so, in fact, you can do a little calculation, and in the simplest case, for the Einstein de Sitter universe, the redshift at which this happens is 5/4, 1 1/4. What that means is, in the standard Einstein de Sitter model, which is a pretty good model of the universe in recent times, anything beyond a redshift of 5 1/4 is looking much larger than it should have done. In fact, for any model beyond there, it is looking the same size as something much nearer. And you might spend a few moments thinking about the following. The furthest we can see is the surface of last scattering. And there is a huge amount of refocusing by the time we hit the surface of last scattering, which means if you have a rigid rod down there, it looks the same as something really quite close. You might like to do as a little exercise. What is the redshift at which the angular size at the surface of last scattering is the same as an object which is actually really quite close to us? That's actually quite a nice little calculation that you can do. So area distances refocus. And they refocus quite close in a Einstein de Sitter universe because by today's standards, that's actually quite close. Now, the third thing is luminosities or intensities. And what you have to do there is turn around your thinking. What you have to do there is think, here is the galaxy, and the galaxy is emitting light which is coming up, and here I am the observer, and my world line intersects there. And what we need to think of is this galaxy is emitting light in all directions. We've put a telescope up here, telescope of a certain aperture, and what that telescope does is it cuts off a certain bundle of null rays. And there's an area to that aperture of the telescope. So when you build SALT, you've got a nice big area compared with all the old telescopes sitting up on the hill at Sutherland. You're chopping off a much bigger solid angle from the light which came down here. And what we can define here, we can define dA is rg squared d omega g. This is exactly the same formula as we had before, but that one was applied to the downgoing null geodesics, and this is applied to the upgoing null geodesics. So you've got the null geodesics which spread out from us, or at least which are arriving at us from all places down below, and you've got the null geodesics here spreading out from one particular object down there, spreading out in all directions. The light from that object has spread out into a huge sphere, and we managed to intersect a tiny little fraction of that light from that object. With just a little bit of thought about photon conservation and so on, you can work out that the luminosity, and the formula is given somewhere in here, the flux we receive up here is equal to the luminosity over 4 pi, 1 over 1 plus z squared, 1 over 1 plus the scale factor squared today, times f squared of r. And that is the flux we receive from down there. This is basically based on photon conservation, that every photon emitted into there is received up here. And there are two factors, 1 plus z, which come as follows. Firstly, photons are being emitted at a particular rate down there by the source, the sun, the galaxy, whatever. But because of redshift, I emphasize redshift is a time dilation effect. We receive these at a factor slowed down by 1 plus z because of redshift. So that's the first factor, 1 plus z. The second factor, 1 plus z, you have to work at a bit, but it's easiest to think of it from a quantum viewpoint. You've got a photon which sets off a particular frequency here. It arrives at a lower frequency here. You lose energy in the photon because of the redshift affecting the frequency. That's where the second factor, 1 plus z, comes from. And this is the area factor saying that the light that went into a solid angle d omega there is received in a solid angle d up there. And this is the basic of the magnitude redshift curves. From this, the magnitude is a logarithmic measure of the flux, and the redshift is there. So if you know the luminosity of the source and you substitute. Now this is what we've called Rg squared. And if you think about this one here, this here is the same as this here, excepting this scale factor is evaluated at the time of emission, and this scale factor is evaluated at the time of observation. And what that means is that Rg squared is Ro squared into 1 plus Z squared. I hope I've got the square the right way up in that. And what that means is that the downgoing and the upgoing area distances are the same up to the factor 1 plus Z squared. And this is what Bruce Bassett was talking about yesterday, that the downgoing null geodesics and the upgoing ones are tightly correlated by what is called here the reciprocity theorem. And the reciprocity theorem says, if you know how areas work going down, you know how they work coming up, because they are simply related by a factor 1 plus Z squared. So these are the three basics, and then the final basics is numbers. And what you do in a particular part of the sky, you look at a photographic plate or a CCD image or whatever, and you count the number of sources you see there. This goes back to Hubble. This is what Hubble was doing in 1934, and it's how he first showed the universe is approximately spatially homogeneous. So the question is, can we get a formula for the number of galaxies that we will see? Now the problem is, this is an integrated set, and what you really want to do is the following. Now we're looking down from the source, and we're looking down, and we're looking at a little volume down the light cone. And that volume may go from a redshift Z to a redshift Z plus dz, for instance. So in other words, that will correspond to dz. It'll have a certain volume, dv, and you can calculate that volume because you know that area, and you can easily work out what that distance is. And so what you can work out is dn is some function times dv, and then dv is minus, it's the redshift actually, the scale factor times the area distance times the increment in redshift. And the details are written down in those notes I've given you, so I'm not going to bother with those details now. The point about it is the following. We can theoretically write down a number there, provided we know the number density of galaxies. So if you know the number density of galaxies, you know the volume. dn is the number density times the volume. And that's the number of galaxies which you should see between a redshift of z and z plus dz. So you can plot these curves of number densities as a function of redshift. And then you can go out and look at a plate and try to count the number of galaxies or radio sources or X-ray sources, whatever they are, and use number counts. And that's the third kind, the fourth basic thing. Redshifts, angular sizes, luminosities, and numbers. Now, we could go into a lot more detail about all of this. In a sense, I will be summarizing the outcome of this afternoon when I talk about the concordance model. But there's one thing which I would like to just say a little bit about, because from here to here, I've made a really big assumption which is not true. What I've assumed is that the number of galaxies there is the number density times the volume. That is true. What is the false assumption? The false assumption is that when you look at the photographic plate, you see everything that there is in there. And that is not necessarily true. We may easily not see all of the galaxies in that volume. I'm now talking about page 129 in these notes. What we need to add in here is a factor p, which is the probability that you will detect the galaxy. Now, you may not detect it, or you may not recognize that it is a galaxy. And this is where life gets really interesting, because there's all sorts of selection effects and detection effects which come in to whether you see a galaxy and whether you recognize that it is a galaxy. And I just want, some of the mathematics of this is written down in those notes. I just want to show you the basic kind of idea. And the starting point is the following question. If you look out at the sky there, where are the stars? Okay, you don't see the stars. Where have they gone to? Where are all the stars in the day sky? Well, they're there. You just don't see them. Why do you not see them? Let's take brightness as a function of angle in the sky. Here's a typical galaxy image. The typical galaxy image depends on the profile of the galaxy, but a typical galaxy image, it'll have a very bright center, and it dies away. There's a lot of evidence, which Prof. Farrell has probably told you, galaxies continue, they fade out, they don't have a nice sharp edge, they keep on and on and on. Now, the statement is very, very simple. There is a background, there is a detection limit. And you can detect the galaxy if it's above the limit, and you don't detect the part of it which is below the limit. Why is there a detection limit? Because there's all sorts of noise. There's noise in your detector system. There's noise in the night sky. And so for any particular, in fact, quite often the night sky level will be quite a lot more than your detector. Through sophisticated techniques, you can see things at a fraction of the night sky level. You just use sophisticated statistics and detectors and so on. But in any case, the basic point is that there is a selection limit. You see the thing. Your detector says yes. If this rises above, and if this is a bit below, you don't see it because it is lost in the background fluctuations in your photographic plate or the shot noise from your CCD detector or whatever. And so, in fact, there can be masses and masses of low luminosity galaxies which we don't detect. And furthermore, what you can see here, the apparent size of this galaxy, if you succeed now in getting much better detectors, much better statistics, you get a much lower detection limit, that galaxy will look larger. It will appear on your photographic plate. You saw it out there, and then it faded into the background. A better plate, you will see it further out. Its apparent size will be a function of this limit. If you get worse and worse detectors, if your detection limit gets worse, you will lose it. And that's basically what happens to stars during the day. They're still there, it's just that the background has come up so much that we don't see the stars during the day. So there really is a really interesting kind of thing going on here. When you deal with very, very deep galaxy surveys or very shallow galaxy surveys, how many things are there out there which you are not seeing? And the key point about all of this is it depends very much on the radius. If you take a galaxy of a particular size, you may or may not detect it. Make it twice as large. Same number of photons, it's twice as large, so the intensity has gone down as the square of the apparent size of the galaxy. And so the size of galaxies, the apparent sizes, is just as important in their detection as the intrinsic brightness at the center of the galaxy. And this is something which needs to be taken into account when you look at all galaxy statistics. And whenever you look at magnitude redshift curves, there's hidden statistics underlying that. When you have angular size redshift curves, the key point is all the galaxies you're not seeing. And that all depends on the detection theory here. There's a bit more about these in these notes. So that's really quite an interesting kind of thing. However, I mustn't spend too much time on this because I want to say something about horizons. I've got two more things I want to talk about now. This evening, I'll be talking about the concordance model and how good it is, evidence, queries about it. And then tomorrow in my final lecture, I'm going to do something quite different. I'm not going to be talking about cosmological models. I'm going to be talking about local physics and the universe, which is quite an interesting topic in its own way. Okay, what I need to do now is move on to section 8, page 133, which is causal properties. So here's our past light cone going down, and there's the surface of last scattering. And the point about it, which I've made many, which I will keep on emphasizing, if you think of the past light cone, here we are. We receive, here is our world line. Here's the surface of light scattering. We can't see earlier because the universe is opaque. There is a maximum radius to which we can see. Now, how do we work that out? We work that out by going to our basic formula over here, this formula here, and the radius function at the visual horizon is the integral from the time of decoupling to the present day dt over at. So this is the time of decoupling. Here's today. The radius out there is given by that little formula there, and you can just sit down and work it out. And this is what is normally called the Hubble radius, or it's normally what's called the size of the universe. I, of course, have told you the universe is potentially much, much bigger than that, but this is what is often called the size of the universe. It's the furthest distance we can see. Now, a galaxy that formed here will intersect our world line, and we will see it at that time in its history. A galaxy which formed closer in, we will see at a later time in its history. A galaxy which formed further out, we will see an earlier time. And a galaxy there, we will never see. We get no information from it because it never intersects our past light cone this side of decoupling. So there is a horizon, and the horizon is the set of galaxies which are the limit between the ones we can see and the ones we can't see. And there is a most beautiful article on horizons by Wolfgang Rindler in Monthly Notices of the Royal Astronomical Society in 1957, I think it is, which is still an absolute classic article, because there was a huge amount of confusion about horizons until Rindler's paper, which very clearly sorted out the fact that we are surrounded by this sphere. We've seen the galaxies inside in principle. The ones here, that's the matter which is the limit that we can reach to by any radiation, and we cannot receive any information from the galaxies outside. And that is the visual horizon. Now, there's a separate thing, which is the particle horizon, which is the integral from 0 to today, dt over at, and that is the limit of causal communication. Actually, I have to say, Rindler's paper was about this, not that one. To get that one, you have to go back down to the time t is 0 and see how far your light cone has reached at the time t is 0. Now, I've already said that the light cone is refocusing, and in fact, at the time of the hot Big Bang, in fact, the light cone comes back to a point, which is actually fairly easy to prove if you think about it. At the Big Bang, the light cone coalesces to a point. So it's rather difficult dealing with all of this until we use a device that Roger Penrose introduced of conformal diagrams. So in order to see what is happening, go conformal. Now, what that means is, here, you ask yourself, can I make this metric conformal to flat space-time? And what you do is you say, I'm just going to look at the radial part of the metric, minus dt squared plus a squared of t dr squared. What you say to yourself is, I'd like to write that in the following form as a squared of t into minus d tau squared plus dr squared. Can I bring that to that form? Well, yes, easy. You just need minus dt squared as a squared of t d tau squared, or two minuses cancel out, so you just need that d tau is dt over a. You just need to change to that conformal time, and this will be your metric form instead of this. Why is that good? Because then the null cone is given to you by d tau squared is dr squared, that is d tau is plus or minus dr. What you've done, you've changed coordinates from coordinates t and r to coordinates 2 and r until your light cone is at 45 degrees, just like in flat space. What that means is you've gone to coordinates which show you the causal relations perfectly. Now, distances are totally misleading. And so you must never believe spatial distances when you're using conformal diagrams. But the causal relationships are shown. What can affect what causally becomes 100% clear. So what happens to the Robertson-Walker models when we use conformal coordinates? what happens is we now choose conformal time tau and this coordinate radius r. Okay, this will be today, and our light cone is at 45 degrees because we've gone to some trouble to make sure that our light cone is at 45 degrees. This will be the time of the Big Bang, this will be the time of decoupling, and this will be the present day. Now, galaxy world lines are still vertical world lines. That is a line r is constant, and our transformation did not affect that. We changed the time, we didn't change the spatial coordinates. So galaxy world lines are still lines, r is constant. And here you get a very, very clear picture of the causal relations. From here down to the surface of last scattering, we receive light down to here, and this is the path of the particle horizon, a particle which is the limit between what we can see and what we cannot see visually. And on the other side, it is over here. And if you put that all together, we are surrounded by a sphere. The sphere is the limit to which we can have seen. Now, what does that correspond to physically? It's nothing other than the surface of last scattering. When you look at those COBE pictures or the map, all of those satellite pictures of the microwave background, you're seeing the sky, you're seeing the visual horizon. That's exactly what you're seeing. The matter at the visual horizon is the matter which emitted the microwave background radiation, because that's the furthest we can see. And that's the visual horizon. The particle horizon is a little bit further out. Further out from the particle horizon, now this is the Big Bang, so you can't continue anymore. There's no space, there's no time, there's nothing below there. So this is the farthest that any causal connection can come from. So, if we can see someday neutrino telescopes, we'll see out to here. Gravitational wave telescopes, we'll see out to here. But we will never, ever see past that horizon as long as special relativity locally remains a valid theory. So the particle horizon is a sphere surrounding the visual horizon. We can have had causal contact with everything up to the particle horizon. We can have had visual contact up to everything up to the visual horizon. We cannot have visual contact any further. We cannot have causal contact any further, unless we live in a small universe. Remember what I said yesterday. So if you live in a small universe, the topology is wrapped around and there aren't any horizons, if you remember what I said yesterday. So I keep on emphasizing a small universe is absolutely 100% different from a universe which continues forever. Okay, if there's a small universe, we've seen everything there is in the universe, and that's fantastic, but that's probably not the case. The probable case is there is this visual horizon and the particle horizon. This now leads to the famous horizon problem. Looking in this direction, we measure microwave background radiation from the point P, and looking in this direction, we measure microwave background radiation from the point Q. So looking in that direction, Q, in that direction, P. 2.75 K from there, 2.75 K from there, which means that conditions here must be very, very much the same as conditions there. Great, what's the problem? The problem is that the past of the point P is that region there, and the past of the point Q is that region here, and that's the beginning of the universe. No causal influence from here can affect anything that happens over there. So why is the universe such that the microwave background there is the same as there when there can't have been any causal communication between them? And that's the horizon problem. Now, there are two attitudes to this. One attitude is to say, so what's the problem? The universe was made that way. And that's all there is to it. And that is the view which some people take, and it certainly was the view which was taken up until 1980. It's very interesting to go to Weinberg's book that was mentioned earlier today and to read his section on the Copernican principle in cosmology. And Weinberg says, and I quote, Weinberg says, "It is inconceivable that we are at the center of the universe," which would be one of the ways in which things could be different. Weinberg takes, and Bondi takes, and all the old books, they justify the cosmological principle on philosophical grounds. And that is the correct way to do it. It can only be justified on philosophical grounds. And you still can go back to old arguments, and if you want to say the reason it's the same everywhere is because it was built the same way everywhere. That's the way the creation mechanism worked. That's all there is to say. However, with inflation, you can say, actually, things change. If you go to an inflationary universe, you see, the standard horizon comes from putting in there A is t to the half. You remember I worked out yesterday the asymptotic form of this in the hot Big Bang area is t to the half. And that's what gives the scales here. If we had an exponential expansion in here, suddenly this integral becomes much larger. And the effect on this diagram, if there is inflation, is to shift this surface down a huge amount. And the effect of inflation is to shift down in this conformal diagram. How does it do it? Because it changes the relation between the conformal time and the proper time. It does it by putting in an exponential there, which makes a very big difference, obviously. And so what the effect of inflation is, it makes no difference to any time later than the end of inflation. So if that's the end of inflation, it makes no difference to anything after that. In particular, inflation does not change the visual horizon. It has no effect on the visual horizon. What it changes is the causal horizon by shifting down the Big Bang from here to way, way down, something like this. And that means that this part light cone here and this part light cone here now have a large area of overlap. And that means you can have some common mechanism which affects both of them. And so, roughly speaking, in a diagrammatic way, this is how inflation solves the causal problem, which has come to be called the horizon problem. Okay, these causal diagrams really do help one to understand very, very carefully how causality works in these Robertson-Walker models. I must emphasize again, the physical distances here, the physical distances are the actual distance you would measure will be scaled by the scale factor times r, and that is going to 0. So remember, the actual light cone is collapsing to a point here. So what is causally a hyperplane is, in terms of metric distances, a point. And people get very confused about that. The causal behavior and the physical behavior in terms of the way distances behave are completely different because they are scaled by a of t, which goes to 0. So the distance goes to 0 even as the causal size remains finite. What you need to remember, the singularity itself is not a part of space-time. Space-time is everything future. That t is naught is the boundary. It is not in space-time because at t is naught the metric has broken down. So this is the boundary of space-time. It is not in the space-time. Okay, well, the upshot of all of this is that the part of the universe we can see is a very small part of the whole universe, and this has important implications. For example, chaotic inflation cannot be tested observationally. Because in chaotic inflation, somewhere way out here, there's a sort of a huge wall or something, and the other side there's a different Friedman-Robertson-Walker model from over here. In chaotic inflation, there are these huge sections of Friedman-Robertson-Walker models with different characteristics. But the point is, this other one is way out there beyond the visual horizon. That means no information of any kind comes to us from that other domain out there. That means that the hypothetical existence of those domains cannot be tested by any observational test. SALT will not tell you if we live in a chaotic inflationary universe or not. It cannot do it because these regions are way outside. And in terms of these kinds of limits, I want to sort of finish off this little bit with just a comment. The ultimate of this lack of causal connectivity is in what has become to be called multiverses. And I could give you a whole lecture on this, but I won't. But the idea that our universe is not the only universe, that there are thousands, millions, even people say an infinite number of other universes out there apart from our own universe. Now, People peddling this idea include Martin Rees, they include Max Tegmark, they actually even include Steve Weinberg. And what people want this multiverse for, all of these other family of universes, is so that you can apply statistics to cosmology. And when you've only got one universe, you can't apply statistics to cosmology because there's only this one thing sitting there. But if you've got this ensemble of millions and millions, maybe an infinite number of universes, wow, now we can apply statistics. And that's what Weinberg and Tegmark and Rees and other people would like to do. So maybe, apart from what we're seeing here, somewhere over here, totally disconnected, there's some more universes, there are other light cones, there's other expanding domains, with no causal connection of any kind whatever, because these are completely discrete space-times. Well, together with my colleague Bill Sturger, we are fighting a little battle with Martin and the others to say, is this science or is this metaphysics? Because if you have a hypothesis like this, in which there isn't even the faintest chance of obtaining any kind of observational evidence, in my view, you are talking metaphysics, and you are not talking science. These various papers by Martin and Tegmark and so on try to say that this is a part of physics rather than metaphysics. And this is a very interesting area of current debate. Watch this space. There's going to be a lot of action in this space between the people who are pushing the idea of a multiverse and the people who are saying that this is metaphysics. Okay, now, I've done as much as I'm going to do about the Robertson-Walker models today, the standard models. I'm going to finish off today by a very, very brief set of comments on other universes, which I've spent a lot of time on because I really enjoy them. As I said this afternoon, in the popular lecture, I will be talking about the concordance model with some criticisms, and then tomorrow I will be talking about local physics in the expanding universe, which is an interesting topic, quite different from what I've been doing now. So the remainder of what I want to do in this talk is just very briefly to talk about other models. So the universe, most of cosmology is based on the Robertson-Walker models. But is the universe Robertson-Walker? Well, I've given you evidence that it is Robertson-Walker within our past light cone down to the surface of last scattering. But at very much earlier times, was it Robertson-Walker? Will it remain Robertson-Walker model at very much later times? Some really interesting work has been done looking at this using the basis of dynamical systems method in cosmology, and a nice book on this by myself and John Wainwright summarizes a whole lot of this work. And I'll give you a brief summary and then say some comments about it. There exist universe models which are observationally indistinguishable from a Robertson-Walker model that are quite different at early and late times. In other words, even if this patch of the universe that we can see from today down to the surface of last scattering is Robertson-Walker-like, there are universe models which are very, very close in that domain, but which are completely different at very much earlier and very much later times. And I'll illustrate this by another dynamical systems diagram coming from the study of inhomogeneous and anisotropic models. This is actually a diagram that comes from Bianchi 2 universes. And what you have is one anisotropy parameter this way and one anisotropy parameter this way. These are what are called the Kasner ring Kasner models. These are vacuum models, which are very well understood. This is the Friedmann-Lemaitre model, and obviously I don't have time to explain all the variables. Basically what I'm saying is this is the isotropic flat Friedmann-Lemaitre Robertson-Walker model. This is a very anisotropic empty universe. This is a very anisotropic empty universe. This is the vacuum boundary, and that is a plane wave state, which is the asymptotic state at very late times. Now, this is for Bianchi 2 universes. F is a fixed point. The Robertson-Walker model is a fixed point, but it's a hyperbolic fixed point. And you get an evolution here from the Kasner model to the Robertson-Walker. You get an evolution there from Kasner to Robertson-Walker. The generic evolution is to go around and end up asymptotic to a plane wave state up there. Now, hyperbolic fixed points have a very interesting property. As you come along here, it's a fixed point, so the arrow pointing along there gets smaller and smaller and smaller, and it goes to 0 in the limit. In fact, as you know from the way hyperbolic points work, it takes an infinite time to travel along there. You never actually reach that point. You get closer and closer, you never reach it. Well, what that means is, if you take this curve here, the tangent vector is very large. It gets smaller and smaller. It gets very small here, it gets larger there. That means that as you travel along here, you travel very fast. You stay a very long time there. You hover there, and then you rush off and approach that space asymptotic state up there. So in this phase plane analysis, if I choose curves that go closer here, they spend longer and longer here, and they are closer and closer to the Robertson-Walker model there. They were completely different to start with, and they're completely different to end with. You can choose a time as long as you like. And there is an infinite number of curves. There's an open interval of curves that spend greater than that length of time, closer than epsilon, to that Robertson-Walker model. In other words, choose a model as close as you like to Robertson-Walker, choose a time as large as you like, and I will find you a one-parameter set of models which start off in a completely anisotropic way, they end up in a completely anisotropic way, and they are indistinguishable observationally from a Robertson-Walker model, because for all of that observational time, they are closer to Robertson-Walker than you can distinguish by any observational measurement. And so this is what we call intermediate isotropization, and this is just to show you that you can actually find out quite fun things by looking at these phase planes for anisotropic and inhomogeneous universe models. If you believe in generality, you see, some people, as I say, believe in speciality and some in generality. If you believe in generality, you have to make the following deduction. In the real universe, this is one mode of inhomogeneity. It's a spatially inhomogeneous mode of inhomogeneity. If you believe our universe is a general universe, which has then been isotropized by a process like inflation, you have to say that this anisotropic mode is there. It is non-zero. And if it is non-zero, it takes over at early times and at late times. And the universe may be like a Robertson-Walker model for quite a long time, but it's not like a Robertson-Walker model near the initial singularity, and it won't be like a Robertson-Walker model in the far future. So this is just the kind of thing which is quite interesting to look at these models. And the final thing I will... Sorry. Very good point. This is for vanishing cosmological constant. Sorry. If the cosmological constant is non-zero, then it'll be different. Thank you. Yes. Yes, I'm still getting used to the idea of the cosmological constant.
5 years now.
The final thing I'm going to give you is give you a diagram which shows you how anisotropic and inhomogeneous models work. And what this is, it's a diagram of how symmetries work. And for symmetries, there are two basically important kind of things. When you have a symmetry, then there's a surface in which everything is the same at every point, because there's an isometry group which moves you around on that surface. Now, the dimension of what we call the invariant variety is then S, and that is the surface in which the homogeneity acts. Now, in a standard Robertson-Walker model, you can have four-dimensional surface of homogeneity. Everything is the same in the whole of space-time. That is S's form. You can have S's 3 spatially homogeneous models like the Robertson-Walker models. That is S is 3. You can have S's 2 inhomogeneous models in which the surface of homogeneity is two-dimensional, like spherically symmetric star models. So S is the scale of the surface of homogeneity, the size. There's a second very important thing. Around each point, there is an isotropy group in general. The isotropy group moves directions around in the sky, leaving everything invariant, and that's what I call Q. And there are three possibilities in general relativity. The isotropy group in a non-empty Robertson, in non-empty universes, I must emphasize this, in non-empty universes, the dimension of the isotropy group cannot be bigger than 3. because your 4-velocity vector gives you a preferred direction, and all the symmetries take place in the orthogonal 3 space. That's a maximum 3. There isn't any 2-dimensional one. Isotropy group can be 1-dimensional, which is the case of local rotational symmetry. There's an axis, and everything is the same around that axis, but it can vary along the axis, and you can be anisotropic. And so this dimension is S, this dimension is Q, and then the group dimension R is S plus Q. And you can classify models according to these symmetries. Now, for the space-time homogeneous, you have the Einstein static universe, which is no good as a model of the universe today, but it's an interesting asymptotic state. You have the Gödel universe when it's rotationally symmetric, and there's a whole family of anisotropic models which are known and are not of particular interest cosmologically. These are the ones which are space-time homogeneous. The spatially homogeneous ones, the Robertson-Walker model is the one that's isotropic and spatially homogeneous. There's a whole family of rotationally symmetric models which have been investigated in great detail because they're very easy to investigate. And there are the Bianchi models, which are the ones I've spent a great deal of time on because they are complicated, but they can be handled still. And that's what that dynamical system book looks at. For the inhomogeneous models, I've lumped, these are the 2-dimensional ones with a 2-dimensional surface of homogeneity. These include, there aren't any here, they can't exist. These are the Bondi-Tolman family, and these are enormously helpful in examining inhomogeneities in cosmology. These are exact solutions with spherical symmetry, but the spherical symmetry, they can depend on space and on time. And a huge amount of work has gone into those models to study things like gravitational lensing, like cluster formation, and so on. And then there's a family of generic models here in which there's no isotropy group and they are inhomogeneous. And we actually know quite a lot about such models, but they're difficult to use because they have such low symmetry. And then there's the ones where there's just a 1-dimensional group, and then there's the ones with no symmetries. And curiously, we have got 3 sets of families of exact solutions of models with no symmetries whatever, exact solutions of the Einstein equations. It's really quite an amazing achievement that we've got those. But then the real point I want to make is that the real universe is here. Okay, the real universe has no symmetries. And whenever we use any of these other models, including the Robertson-Walker, to model that, we must remember that this is an approximation, and the real thing is not in any of these categories. The real thing lives down there in the space where there's no isotropy and there's no spatial homogeneity. Okay, that's what I wanted to do now. This afternoon I'll be talking about the standard, the concordance model and its coherence, and tomorrow, just for fun, I'll be talking about local physics in the expanding universe. Yes?
I agree with you strongly that things like multiverse and tropic principle do not belong in science. So I applaud you for saying that. So let me ask you a question. Do you think the anthropic principle is falsifiable?
Is the anthropic principle falsifiable? No.
It's not falsifiable.
It has to be used as a selection criteria.
Well, let me ask you this.
Well, when you say the anthropic principle, it's like saying is Mach's principle falsifiable. There's so many formulations, we have to discuss which particular formulation we're talking.
Okay, and let's say a moderately reasonable formulation is anthropic principle. And now I'll try something out on you. I gave a talk at a neutrino conference earlier last year in Australia. And my talk consisted of the following. The present data on the neutrino mixing matrix looks very much like it's a very special matrix with entries like 1 over square root 2 and 1 over square root 3, things like this. Now, of course, that can never be decided experimentally, because experimentally it will always be just some number with some error.
Right.
Now, the question I have is that if, and as far as I know, and as far as anybody knows, I think nobody claims even the strongest anthropic principle advocates would not claim that neutrino mixing has anything to do with human existence. Now, if the theorists in this field, neutrino theorists, work very, very hard and manage to derive this special matrix,
Yes.
would the anthropic principle be falsified? Or they just say, because
it's got nothing to do with it.
Right, and because in different universes, presumably, those people would say it's just a random accident. But then they could always say, well, no, there's some deeper principle that would give this, and so on, comes out of, the nth successor of string theory, or whatever.
All right.
Is it falsifiable if neutrino physicists were to work hard?
Well, the first point I would make is you must be just a little careful assuming that this neutrino mixing does not have to do with the existence of life, because it might have to do, for instance, with the amount of radiation given off by the sun or by new supernovae. And it's not impossible I would find a link through there to the existence of life. Yeah. No, all you're saying is, I don't think it would disprove it. I think it would simply say it doesn't, the anthropic principle shrinks the possibility space, but it doesn't shrink it to one point. It just shrinks it to an open domain, and I think that's absolutely fine. So I don't think you would disprove it that way. The most important use which has been made of it in a practical sense is Weinberg's use, which he's trying to justify the present value of the cosmological constant. Now, that is really extraordinary, because he's kind of admitting that sort of a distribution of cosmological constants would be huge, and then there'll be this tail. And in effect, he's using the anthropic principle to say we're way out in the tail over there in the real universe.
Well, that's Vilenkin's criticism, that everything depends on the finite distribution.
Yes. Yes.
But on the other hand, I find Weinberg's use actually acceptable to me, because it's relatively mild, right? It's using an experimental fact, which is, in physics we use experimental facts all the time. He's using one experimental fact, namely that galaxies exist.
Yeah.
Why not? What is your objection to that?
I don't object to that at all. The problem is that he explicitly states that there is an ensemble of universes, and he talks about the various ways it could happen. It could be multiverses in the quantum kind of way, or it could be chaotic inflation, or it could be disjoint. So it's very, very vague at that point. And then the point simply is that there isn't any evidence that any of these other universes exist. So sure, you explain. It's a device to explain what is in fact incredibly improbable by manufacturing in your mind this ensemble of universes. Now, manufacturing in your mind is one thing, but to claim that they actually exist out there is a totally different point.
Well, let me give you another example. 300 years ago, I could have used the anthropic principle to prove that the Earth must be flat. Because if it isn't, we will fall off. And we wouldn't exist. Now, do you accept that as an argument against anthropic?
The anthropic principle will always be phrased within your knowledge of physics of the time, and within your knowledge of physics at that time, that would have been an acceptable use. What has changed is the interpretive framework within which you're applying it, and that will also happen to us.
Okay, well, it's very hard for me to argue with you because we're on the same side.
But let me use this opportunity just to say one other thing, which I really... with my friend Bill Sturger, we've put an article on, and Uli Kirchner, who is here, we put an article on multiverses on the web, in which we make the following point. Many of the people who talk about multiverses talk about infinities of universes. Now, I have a real problem with the idea of infinity of universes. And we give a lovely quote from David Hilbert, who says, infinities is a nice mathematical idea, but it is never realized in physical practice. And I think that's a really interesting thing to talk about. It relates to what you were saying earlier. Yes, it relates to the cutoff, precisely. Because, in fact, the mathematical continuum which underlies theoretical physics, I think, is not a real thing in physics, and that's what you're saying. In fact, that there's a quantization which cuts off that. And I think you might find this quote by David Hilbert really nice, because he really says that infinity is a nice conceptual idea, but it never occurs in the real universe. And it gives the cutoff in exactly what you were saying. So we're agreeing in that. There's a real problem with the claim that there's this infinite number of universes, because infinite is infinite. It's not a large number. If you take seriously the idea of all that can exist exists, which is the phrase that they use. Okay, so now think of a Robertson-Walker model with a given density parameter, and then you've got to take all values of the Hubble constant for that density parameter of everything. That is an uncountable infinity of universes out there. It's uncountable. It's mind-boggling that people can think this actually exists. And there's a very, very nice little book by Martin Gardner recently come out called On the Multiplicity of Universes and Blackberries, or some title like that. And at the end, he has a very caustic comment on the scientists who are out there suggesting there is an infinite number of other universes. He closes it off by saying there is no more evidence that there are two universes. There's no evidence even that there are two universes, let alone an infinite multiplicity of them.